Okay, here we have the acid-base question that came up in the 2016 paper, and you can see it came up in question 10, part A, so it was a nice little question worth 25 marks. So the first thing that they ask us for is to distinguish between a strong acid and a weak acid. But they don't differentiate between Arrhenius or Bronsted-Lowry. So they will actually, or they did actually accept either of the definitions. So I'm going to go with the Bronsted-Lowry definition of a strong acid. So I know that that is a good proton donor. And we know that a weak acid by the Bronsted-Lowry theory is a poor proton donor. You could have also used the Arrhenius definition, which says that a strong acid fully dissociates in water to produce hydrogen ions, whereas a weak acid only partially dissociates in water to produce hydrogen ions. So let's have a look at the next part, part 2. So they ask us to calculate the molarity of a sulfuric acid solution that has a pH of 2. Okay, so here we're working backwards from the pH to figure out the original molarity. So I'm going to use my equation for pH, which is minus log to the base 10 of the hydrogen ion concentration. I'm going to put that equal to 2. Then I'm going to bring the minus sign across. I'll use the inverse log, which is power 2, and that gives us an answer of 0.01 moles per litre of that hydrogen ion concentration. Now let's take a look at sulfuric acid, because we know that sulfuric acid, it's a strong acid. It fully dissociates to produce 2 hydrogen ions for every 1 molecule of sulfuric acid. So we've got a 2-to-1 ratio here in terms of for every 1 molecule of sulfuric acid, we get 2 hydrogen ions produced. So that means that if I've got 0.01 moles per litre of hydrogen ion produced, it has to have come from half that amount of sulfuric acid. So that gives me 0.005 moles per litre of the sulfuric acid. So the concentration of my sulfuric acid with a pH of 2 is 0.005 moles per litre. Now the next question asks us to calculate the molarity of a solution of a weak acid that also has a pH of 2. Okay, now the difference between this monobasic acid and the sulfuric acid is that it's weak. So that makes our calculation a little bit different. But we already know so far that a substance with a solution of pH of 2 has a hydrogen ion concentration of 0.01 moles per litre. That's what we figured out in the start of the previous calculation. Now what we need to do is use our equation for a weak acid. So we know that the hydrogen ion, or the amount of hydrogen ions in solution of a weak acid, depends on the dissociation constant and the molarity. So this molarity here is what we want to calculate for our weak acid. So I know that the concentration of the hydrogen ions is 0.01, and I'm also told in the question what the Ka is. So I've got 1.8 by 10 to the minus 4 multiplied by the molarity of my acid. So I'm going to square both sides. And then bring that dissociation constant across. So that's going to give me an answer for the molarity of my acid to be 0.05 0.556 moles per litre. So that is the molarity of my weak acid. Now the final question asks us to define Kw, the ionic product of water. Okay, so we know that Kw is the concentration of the hydrogen ions multiplied by the concentration of the hydroxide ions. Now they're telling us a value for Kw at a specific temperature, and they're asking us to calculate the hydrogen ion concentration of pure water at this temperature. So what they're saying is that the H plus concentration times the hydroxide ion concentration is equal to 9 by 10 to the minus 14. Now we know when water ionizes, the hydrogen ion concentration is equal to the hydroxide ion concentration. So if we sub this hydroxide or this H plus in for the hydroxide, basically what we're doing is we're squaring the hydrogen ion concentration. So let's just rewrite that as H plus squared is equal to 9 by 10 to the minus 14. So in order to find the hydrogen ion concentration, we're going to square root 9 by 10 to the minus 14, and it's going to give us 3 by 10 to the minus 7 moles per litre of our hydrogen ion. So that was a nice little 25 mark question in 2016.